Today we're talking about new systems for managing mathematical knowledge that could really be as transformative for the public good as the kind of examples that I've been talking about. And there are people who say that Wikipedia has been the greatest public good in the history of mankind. We really do have a chance to do something great here and to chart out something terrific.
Well, I think this workshop was originally my idea, good or bad.
This workshop is on the semantics of mathematics, which is an important, extremely crucial element of what we hope will become this global math library. But of course, the global math library has many more things. This is an exciting part of it because there's research and ideas going on and there's stuff to be constructed.
We've been quite successful in kind of making computable, making computational lots of kinds of mathematics. And I got curious about to what extent we can make all of mathematics, including very pure areas of mathematics, somehow computational. And so I was interested in kind of collecting some of the leading math and maybe meta-math people to understand more about what's possible in these directions.
This conference is discussing the prospects for a digital mathematical library and digitizing mathematics. And to some extent, that means having to set a standard. Rather than having everybody use their own language, agree on some common language or some common formats that we can use to exchange mathematics.
Finding a way of expressing mathematics properly in a formal system has been my main research topic for the past 10 years. And I really want to see my work and the lessons I've learned during that work profit to the largest possible community. And this workshop seemed the perfect opportunity to just do that.
It brings together 40 people from many different areas of mathematics and also from many different views of mathematics.
It's this very interesting workshop on the semantic representation of mathematics, which is of interest essentially for every mathematician, I think, but in particular for somebody like me who has been working on computation and in particular on symbolic computation. Ideal would be that we all agree on how mathematics is to be represented by computers. But that is a goal that is far away to be really realized. What would be good if we could identify small steps towards reaching that goal and agree upon how we can get there and how we should do that.
Let's think about where is this consensus about technically what we can accomplish and how we can accelerate discoveries in mathematics. And let's work together in that kind of a public interest spirit and see what we can do.
So I think it will be important to have a central format for communication, and that's the kind of thing that we're trying to work out now. People are coming together with different foundational attitudes and views. We're getting a sense of what the tensions are. Well, if you do this, it's harder to do that. We're all coming to a shared understanding of what the range of options are and the difficulties are, so that at least we can start talking constructively about how to compromise and where the balances should be.
The way we pass knowledge on has traditionally been through human language, through natural language, writing things down, explaining things to people. In modern times, we have an alternative. We have computer languages, we have precise formal languages. Mathematics is a great candidate for something that should be capable of being communicated through a precise formal language. It's already done a little bit of that itself, but it needs to take kind of the modern ideas that have come from computation and computer languages and be able to make use of those as a way to encapsulate the sort of heritage of mathematics as something that can be propagated into the future. What we hope to kind of take a step towards at this workshop is figuring out how such a language could be constructed, both what it might be like from a technical and structural point of view, and what the human processes around constructing it might be.
And I think it is the first time that we had this atmosphere of seeing the various perspectives together and I'm pretty sure that this will be a kind of very fruitful cornerstone for the next few years in our joint research.
Well, there are many benefits that goes with this workshop, some of which are realizable in the near future, some in the very far future. And I think the trick is to come up with ones which have various prospects, near term, medium term, long term, and to get clear about which is which. People are still living in their own separate worlds, including me a little bit, and we're not on a common page yet.
I think the kind of collaboration that perhaps this workshop has led to is really between the theorem proving people and the computer algebra people. Because I mean, seen from outside, we both look as if we're doing similar things. I mean, we're both doing symbolic computation, we're both doing formal mathematics, and yet, you know, there's some sense of never the twain shall meet. You know, we really have often lived in different communities, and the kind of mathematics we're focused on tends to be different. The computer algebra people focus on things where there's some clear notion of computation, at least, like this expression is equal to this expression, or even this things like this. And the theorem proving people are focused on more sort of abstract quantified statements, you know, for all something there exists something else, such that this kind of topological space is so and so. We can both learn a lot from each other.
The thing which has been researched and dreamed of for at least 50 years now is how to represent mathematics in a computer in such a way that it's very easy for the human to interact with a computer. The computer understands exactly what the human means. It can proof check it, and it can even help with some simpler proofs, for example. And we don't even have the representation language for that. The community has been trying to create over the past decades is a language and a model of interaction between the computer and the human in which they could collaborate and they could do mathematics together.
The workshop has this grand vision at the horizon of a system that does everything, and we need to do some specific things to make some progress. Of course, it is possible to combine the good things from the computer algebra and the good things from the interactive theorem proving and the good things from the mathematical knowledge management into one smooth, nice system. I don't think it's even hard, only it hasn't been done yet. But I think this is something you want, a system where you both get the power of a system that does all kinds of things for you, and the crystal-like solidness, the clarity of the purely formal world. So this is a system that's basically the best of everything. So the mathematics is totally pure, and you have all the computational things that you have in these other systems, and you have a nice integration of text where you have the mathematical paper that you as a human can read and relate to, but the statements in that paper match the statements in the formal developments, and it's all hanging together in a nice way. I'm sure that will be there.
So each one of these things, like a backslash kappa or something, that's a defined thing somewhere else. There's some definition of that somewhere.
Yeah.
Some other. This is what we're kind of talking about here, is taking, you know, a textbook piece of math and turning it into something formal.
Yeah.
So this is a real example of that.
Yes.
And how big is the, you know, how many pages of textbook got turned into? Because this looks like something that's
200. That's the Veit-Thomson proof, and there's about, so it's 200 pages, and there's about 3 times as much in background material.
Okay. So this, for example, looks comparable in length to the, you know, to the textbook thing that you just showed.
Yeah.
Is that typical? That the formal version, as you have formalized it with your set of definitions and your hierarchy?
Yes, that was my goal, and I didn't stop working until I got it.
I see. So your hierarchy of definitions succeeds in making the representation of a particular page be comparable in size to the
for the statements, the proofs. Sometimes I break it, sometimes I break even, sometimes I'm better, and
on average, I probably have still the point factor of 4.
It's not surprising that the statement in Coq looks like the original statement in some sense.
Actually it is.
Yeah. It seems very surprising to me. I think it's a big achievement that it looks
It really is.
The original proof that was given will not be similar to the proof you're going to produce in Coq.
The proof in Coq in this case has quite a bit more detail.
Always, all proofs in formal system will have more detail than the proof given on the piece of paper.
So here it's about, you still have about a factor of 4. If I had had clever automation to work with, I could probably bring that down to a factor of 2.
Mathematics is probably the single largest artifact that's been built by our species, by our civilization. I think it's taken about a million person years of work to produce kind of the tower of knowledge that is modern pure mathematics. My interest in this mathematical heritage project is to try and find a way to bring into the present time, into the 21st century, kind of that body of intellectual work, and to create something that is really useful going forward, and that's able to be presented in a fully computational, fully computer usable form.
And there are different mathematical schools in different countries, so in different groups of people. Some do understanding by abstraction, like for example by Key School. I was originally raised in Russian school, so usually do understanding by working out a lot of examples. You can have an understanding by physical intuition, but then of course it's a question, what is physical intuition? Of course, understanding is the goal of all sciences, but well, like in mathematics, then there is this 0-1 criteria at the end, whether you have a proof or not. So of course at the end a proof comes, but understanding might be much more important.
There's a great opportunity to provide a wonderful service to the mathematical community at large. This is a dream that has existed for a while and it never quite realized, but that much more is possible now. We can digitize documents, we can do optical character recognition much better than we could. People have also an idea of how to build a way of searching formulas and searching for them in mathematical text, and that could then develop into a very interesting tool.
Mathematics is in the center of the current scientific and technological revolution and evolution. So it is very important to collect and condense all the mathematical knowledge that was generated over the centuries and put it into a form where everybody, in particular scientists, but also everybody working in applications, can have quick and reliable access to all this beautiful knowledge.
Maths is probably the academic discipline with the longest tail. We regularly cite papers that are 50 years old, and they are still important, and they don't get out of style. So we need our history, and important ideas are coming from that.
Different meanings for semantic capture. Whether we want to capture exactly what was written as written at the level of formality and correctness that was in the paper, and at the level of formality and correctness, I mean that if the paper's wrong, we still have to be able to capture it. There might be something useful in it, and even so, we may want to be able to capture different sets of things. For example, capture the definitions only, capture the definitions and the theorem statements only, capture the definitions and statements and the proofs, or capture definition statement proofs and meta-statements about what's going on.
30 years ago, when I was working at the École Polytechnique, I noticed that the standard Cauchy bound on the roots of polynomial behaves badly with respect to scaling. If you scale the polynomial so as to double the roots, then the bound multiplies by 2 to the degree of the polynomial rather than just by 2. That doesn't matter for sensible, humanly posed problems, but it's a worry for computers, who may not pose questions sensibly in the same sense. Reading the collected works of Cauchy, I found his bound, and then another on the same page which behaves much more sensibly. Tracing it back via de Mazure, my boss at Polytechnique, Vendelin, Henri Carton, who looked at the notes of Élie Carton, we see that the second inequality was lost before 1880. Yet it's in many ways more valuable than the first. It's now implemented in many computer algebra systems, so it's used by many across science technology, most without knowing it. Hence some importance, I think.
Well, there's no branch of science that is so cumulative in a sense in nature as mathematics is outside of mathematics. So that makes for mathematics accessibility of these old papers really crucial.
Bourbaki, in some areas, they were extremely successful, and what is interesting that out of this thing, trying to sort of understand better the foundation, I think some of it inspired also the new mathematics, especially like algebraic areas like algebraic geometry. On the other hand, they were less successful with other areas. I think they missed some points of analysis or probability, and so they have an interesting book on theory of real functions, but they somehow tried to put it in the common denominator with algebra, missing some of the sort of different ideology. But it's a great series of books, and I'm not sure it's possible to try something similar today, or that one should, but certainly it's an interesting thought.
What is the Global Mathematician Library? So the ideal for what we want to achieve, in my view, is that we provide logic and software systems that are able to support semi-automate, maybe not automate, semi-automate with some interaction, the entire mathematical theory exploration spiral in this meta-mathematics style. But this dream is dreamed again and again over the centuries, and maybe Leibniz was the first with his wish of ars inveniendi, meaning the art in mathematics to invent new things, and ars judicandi. Ars judicandi was decision making, and so the two aspects of mathematics. And so I pointed out in the future, next systems, we must have systems where we have algorithms and theorems in the same system, and this is exactly what we try to do now, and I find this so exciting. I'm so glad that I can still be active part of this wonderful evolution.
Now, what do we get out of the fact that we can that we have this linking between theorems and definitions and sources and so forth? Well, you can ask for theorems by topic, right? So continued fraction theorems that hold for regular continued fractions, for instance. You can find theorems by author, by date, theorems that apply to a given mathematical expression. So here's sort of one example, continued fractions related to Hausdorff dimension. Right? I find it rather fascinating that there would be any sort of connection, but you can see sort of the first theorem that we present sort of a summary of indeed gives you an estimate in terms of the Hausdorff dimension.
I mean, the idea is to have a central repository of mathematical knowledge. So theorems and definitions, right? You can sort of look it up online. And for that to happen, there needs to be a format for that online information. Now, what might you want to do with that? Well, you might want to search for a theorem. You might want to, you might think, you might have discovered something and say, is this already known? You might say, here I'm trying to prove a theorem. I need this fact. I don't know if it's true. Can you help me?
The idea of semantic representation of mathematical results in a digital library is really amazing. It will be very useful, not only for mathematicians. Being myself a theoretical physicist, I think will be also useful in physics. When you are given a physics problem, frequently you don't know yet which type of mathematics you will be needing, so you are forced to explore several areas. It will be great to have a resource that tells you or helps you deciding the direction to go.
So what are some of the goals that we might have? What would we do with a mathematical knowledge base? For example, this was a nice, some of these are stolen directly from Tim Gowers from his talk at our session last month. Determining whether a result is known when you really hope it's not known. You've got a badly needed gap in the literature. Okay, or determining whether a result is known, and you say, well, you hopefully want it to be you want it to be known because then you need it to do something else. More generally speaking, accelerating the advancement of mathematics or of the learning of mathematics, enhancing collaboration amongst groups of people, making existing software tools more powerful, or avoiding unintended duplication.
And there was this article by Billy and Tanner in Notations saying, wouldn't this be nice if we have, it was a bit nice to formulate, we have a mathematician M who has proved the theorem T, and he wants to know through a quick lookup, is there a version T prime or T tilde that's sufficiently near in the literature? And I think it would be a great tool to have such a thing.
Well, the two big developments I see as being needed here are organizational and methodological. So first off, there ought to be a framework for organizing mathematical knowledge. And secondly, there should be a method for reorganizing the extant body of mathematics within that framework.
And to give at the end some scale of what's ahead of us, there are an estimated 100 million pages of research mathematics out there in the world, cumulative, in the order of 4 million papers and books. Math Science currently adding pretty much exactly 100K papers per year. Current doubling time for mathematical knowledge pretty much fitted exponentially, working pretty well is 15.8 years. Number of theorems, that is interesting. There's no good estimate I've ever seen. Of course, it's difficult because especially older papers do not actually say what is a theorem. They just have a long text of interesting material in the order of 3 to 5. Number of named structures, and we will probably hear from Nikita more about it, in the order of 10 to the 5, maybe 2 times 10 to the 5. And how much time would it take to build a decent ground library to get started for some more formal version, according to Freak, in the order of 140 man years.
Right now, there are a number of formal systems out there. There are systems based on set theory, something called type theory. There are many variants of type theory. There are categorical foundations. To a large extent, they're interinterpretable. So anything that purports to give you a foundation for mathematics should be able to make sense of the full range of what mathematicians do. And so it tends to be the case that, from any one foundation, you can sort of understand what the other one is doing. But nonetheless, they're different languages, and they model different aspects of mathematics. And the question is to how to bring them together. Really, the first step is, if you're going to have the computer help you do mathematics, is having a language, having the right language, having a language which you can communicate the mathematics to the computer, and having representations that the computer can then work with. It sounds almost antithetical to the mathematical spirit to sort of impose a monolithic, say that you will use this notation, or you will write things this way. So I think that's not what we want to do any more than we have to. But at the same time, again, it's a serious coordination problem. So I think the challenge is to come up with a central standard that everybody, or most people, will at least agree is reasonable, and then find some way of managing it.
An important part of the mathematical invention. So we should not force all mathematicians to use the same logic and the same build-up of mathematics. As a matter of fact, the essential higher results then, the higher we go, the more similar, so to say, the results become, even if we start from very different approaches.
When you ask people, what's the official foundation or standard for mathematics, one common answer is Zermelo-Fraenkel's set theory. Set theory is a foundation that was developed in the early 1900s. It's very powerful, very expressive. It is possible to represent almost all mathematics in this language straightforwardly in very natural ways. And so it's quite a good foundation. In set theory, officially, there's only one type of object, namely sets. It sounds strange. I mean, no, in mathematics we have all kinds of objects. We have numbers and functions and groups. And one can imagine that for some purposes it would be helpful to have a discipline where, rather than just saying you have one type of object with lots of different instances, you can say, no, there are many different types of objects, and we can keep track of what's what. For example, you can overload notation. You can use the plus symbol, and knowing whether you're working with numbers or real numbers or some additive group, the computer can infer which plus symbol you mean. Whereas, strictly speaking, in an untyped framework, you couldn't do that. You'd have to, there would be this plus, and you'd have to provide the information yourself.
I believe simple type theory would be a far better target logic. It is much closer to mathematics practice, much easier to apply to real-world problems, and provides the student with a more expansive understanding of the logical principles inherent in mathematics. Simple type theory is not much harder for students to learn than first-order logic, since simple type theory is based on pretty much exactly the same ideas and principles as first-order logic, with one exception, the notion of a type. Simple type theory is also an excellent stepping stone from classical mathematics to constructive mathematics and dependent type theory.
The incipient form goes back to Frege's Begriffsschrift from 1879. So there's been a venerable history. Russell and Whitehead's Principia Mathematica, so published in 3 volumes between 1910 and 1913. That was a form of type theory, and so it's as long, in a sense, even longer than set theory. There have been versions of type theory around. I mean, I tend to think of it as a pragmatic layer on top of set theory. Even if you think of all the objects, everything really is a set. You want to have bookkeeping, you want to have notational ways of keeping track of which things are which and how you mean to use them. The observation that started homotopy type theory is that one can also interpret types as spaces, like topological spaces, and the expressions as being sort of continuous dependencies between them. And so, you know, in logic, one typically studies formal axiomatic systems and their semantics, their interpretations. And so to characterize homotopy type theory, there's a class of formal systems, and there is a class of models and interpretations in these topological terms. And one reason that it's hard to talk about is that the field means different things to different people. I mean, there are a lot of different perspectives on it. I mean, one perspective is that it's a system that gives you a tool to support reasoning in algebraic topology, an important branch of mathematics. And it does so by giving you a language where core topological notions are primitives in the system. Right? So built into the system, you can reason about spaces and continuous dependencies between spaces and points of spaces and paths between those points and so on. So that's one interest. But another interesting thing that's emerged is that from this perspective, one can interpret ordinary set theory. So coming back to the computational interpretation, homotopy type theory, Vladimir Voevodsky, one of the founders of the discipline, showed that one can add to the system an axiom called the univalence axiom. It's an axiom that says, roughly speaking, that if you have two spaces that are isomorphic, then in fact they're equal. They're the same from the point of view of the system, which means that in particular, anything you say about one, you can say about the other. So this is a very strong invariance principle.
In mathematics, you do forward mathematics. You prove theorems from fundamental axioms. In reverse mathematics, you prove fundamental axioms from theorems.
Views of mathematics, categorizing mathematics from the point of logicism, intuitionism, and formalism. And then the ontology becomes weaker if you go from left to right, but computational part becomes more important if you go from left to right. And what I'd like to stress here is the fact that most of the proof assistant system we have nowadays mainly based on set theory and type theory. But my proposal here is to stick to finitism. So ontology is weakest, but computation is really essential. So within this finitism, how can we really formalize mathematics? And my view is instead of set or type, I would like to use class.
What I'd like to do here is tell you about something called dependent type theory, and then argue that dependent type theory provides a practical foundation for mathematics, that it's good to use for the goals that we're after.
All you've got is the lambda calculus syntax. You have abstraction over function, abstraction over type, that's the lambda and the pi.
You have application. You have the star and the box. Star says, I'm a type, and box says, I'm the top. I'm a kind. And then you have variables, and that's it. This is everything. Battery on the calculus, type, or everything there. And then here is what distinguishes them. Only one rule distinguishes them. The rule that distinguishes them is the formation rule. It says, so I will come back to that. That's the only, so look, all of them use the simple type rule, star star. How they differ, the dependent rule, you need the box star. The polymorphic rule. The dependent rule, you need star box. Here we are. We've got that. Great. But where do we stop? Because this doesn't, all these type systems, they don't really, we need to be able to play with different type systems to be able to represent different parts of mathematics. So how do we change the system? And every time we change the system, we need again to guarantee all these properties. And here we are. There was a big, when I say Church versus Curry typing. So all I've talked about so far is to do with Church syntax of types. Church syntax, where he put the syntax like that. Everything had to have the type. Look at the syntax. So lambda x is of type A and pi x is of type A. So he took everything to be explicitly typed. Could I actually have a similar kind of hierarchical structure where I'm working with types a la Curry that is implicitly typed?
And so the attraction of dependent type theory is that you really have one language that does it all. So in simple type theory, you distinguish between, there are types, there are terms, then you start writing down formulas or asserting propositions and then proving things about them. In dependent type theory, the language is flexible enough to give you all of these things at once. Right, so we've already talked about, types and terms. How do you encode propositions? Well, quite simply, you just add a type of propositions, and you think of, constructors like and implies as just functions that take propositions and return a proposition, right? So if you ask the system, P and Q, what type of thing is that? The system comes back and says that's just a proposition. Okay, but the point is, so once you have dependent type theory, you have a language that does everything. And so here's how it works. So, everything is a term, right? But so the types are the terms of type. Then a term is, term of type T is just a term. Propositions, things of type prop. And then a proof, you write that as a term that has type P, where P is a prop.
If you want to construe propositions as types, you can say forming a type gives you the problem of saying, do there exist any elements of that type? So asserting a type as a proposition means asserting that something belongs to the type. Therefore, you can construe cross plus arrow pi sigma as logical operations there. And so this gives a really very elementary model to check out all the properties of Martin-Lerf type theory. An example would be saying, finding an element of that last type there at the bottom means you're showing that F is a associative operation.
So the layperson thinks that mass notation is difficult, and the French phrase is pour moi c'est de l'algèbre, meaning it's horribly difficult. I, of course, have great joy here, being a French-speaking, Greek-speaking algebraist. I have no problems with anything. And it's universal. Science fiction stories are full of issues of humans being aliens by doing mathematics, often Pythagoras' theorem or something, and so on. And it's precise, and you can Google the phrase mathematically precise or its equivalent in other languages and get lots and lots of hits. And it's unambiguous. Now, a mathematician, of course, takes slightly different views. It's clearly not difficult, in fact, it's helpful. And the mathematician will probably quote Bourbaki or some variants on this, saying, well, of course, we actually do have to abuse notation, because that's really actually using it to its most powerful. There's the line between use and abuse is a very fine one indeed. Informally, a very fine one indeed. It's pretty much universal, though we've probably all got a little horror story somewhere about how it wasn't quite as universal as we thought it was. And it's precise, because otherwise we wouldn't use it. And it's unambiguous, quite clearly. So what happens when some awkward pedant like me starts pressing a mathematician and saying, well, is 1, 2. So what is that? Is that perhaps a permutation in cycle notation? Or an open interval, at least if you're Anglo-Saxon? Or is it a row vector? Well, you might put commas in. I can ask you the same question about column vectors. Is that a binomial coefficient or a column vector? Or is it an ordered pair of integers? And at that point, the mathematician says, well, okay, it's unambiguous in my context. So in fact, we've gone back slightly. We're going to say it's locally unambiguous, and that's okay for us. Or is it?
So this is a point. I think this is impossible to accomplish in a satisfactory way without actually improving. This is why this is politically incorrect. Without actually improving systematically on existing mathematical notation. Just because some of that notation evolved doesn't automatically think that people had the freedom to replace it with something better without getting fired or killed. So the overhauling of existing mathematical notation is going to require a lot of creative, logic-oriented new ideas if it is going to really be an improvement. Remember, it's got to be an overhauled notation with an absolutely precise semantics. It's absolutely needed for this. I have some confidence in the end it will result in systematic improvements over existing notation, make a digital library the kind people are envisioning more feasible. I now want to delve into the approach.
Some basic words mean different things to different people. So what does the word equation mean? Well, the word equation was introduced into the English language by Chaucer in 1391 or thereabouts, after which Robert Record introduced the equality symbol about 500 years ago. And then Descartes introduced the notion of using variables in about the 1600s. And then a certain bunch of people in the world started to say that equations have to have variables, although variables, the concept didn't exist when the equality sign was introduced. And so now we have, for example, these here 3 different things. This is x to the 4th minus a equals 0, something which is true for some values of x. This can be true for all values of x. This doesn't have any variables at all. In English, 1, 2, and 3 we could call an equation. In some languages, 1, 2, and 3 must be called by different words, and they're not equations. So English and Latin would use A, but Chinese, French, German, Russian, and so on would use different words for these 3 different kinds of things. And actually, it's undecidable then whether something is an equation or is an identity. So even some basic concepts, what could be more fundamental to mathematics than an equation?
The formal languages that we have now for expressing mathematical statements do not support generally readable output. One reason is that many have been designed to support something much more demanding, formal verification. The situation can be changed by devoting more resources to more limited projects. I like the idea of more researchers focusing only on expressing statements, striving for high standards of readability. This involves research on the creative improvement of mathematical notation.
As I said, this theorem construct does not yet exist in the Wolfram language. It is an example of how we could do this in the Wolfram language. First, we need to have the premises and definitions for our theorem. Then we need the conclusion, and then we will have metadata. So first we will have a list containing declarations, assumptions, and definitions for our objects. These objects can depend on previous objects, so the list is read from left to right. For example, some assumptions may contain objects that have been defined previously. Then the conclusion will be a general proposition using the predicate language of the Wolfram language that allows you to express anything. And then a third argument takes metadata, which is information useful for indexing and describing properties of the theorem. For example, you could store the area, the name of the author, the year in which it was shown, references, etc. For example, this is how I would write the previous result I showed as a theorem expression. It has 3 parts: the premises, the conclusion, and some optional metadata. As premises, we have that n is a positive integer, then m is a differentiable manifold of dimension n over the reals, which is a smooth C-infinity manifold. We use colon equal to express a definition. The symbol Tm is defined as the tangent bundle of the manifold M. We also declare a collection of indices, A, B, C, D. G is a metric field on the tangent vector bundle Tm, and its Levi-Civita connection will be called CD. We define the Einstein tensor of the metric connection using indices. It is this particular combination of contractions of the Riemann tensor. The theorem states then that the divergence of the Einstein tensor is zero, as we show it. Finally, we have a list of metadata fields. The theorem is known as the contracted second Bianchi identity, which was stated by Luigi Bianchi for the first time in 1902.
Frank Wiedeck made this observation that the ratio between the lengths of the formal texts and the informal texts often tend to be around 4. That is, strictly speaking, what he was comparing was the source for a sort of LaTeX form of, say, a mathematical paper or a document, and the formal proof script, and both of them gzipped to give you a very sort of crude sense of information content, because, you know, whether you write, say, ASM rewrite TAC or ART, it's really more of a sort of presentational thing. It doesn't really give you any concrete idea about informational content. So as a very crude way of flattening out that kind of distinction, he would gzip them, and then he would compare them, and he would often find the ratio was about 4. My own experience has been that that is quite a typical number, but I think it tends to be different if you formalize mathematics at the graduate level, which is often much sketchier and takes for granted that you know so much more. And so in situations like that, the de Bruijn factor tends to work out very high, because the informal text says, well, it's obvious.
My talk was titled Big Proofs, Little Math, and it tried to convey the idea that small mundane mathematics makes a big difference to how one can be able to achieve large formalization. And this is very relevant to what this workshop is trying to achieve, in that this small mathematics concern mostly how one interprets mathematical notation. I got that idea through, but mostly the audience was very enthusiastic about the actual size of the things I'd formalized. Indeed, there was much discussion during my talk.
And the reason is quite simply that, you know, we can make mistakes. So in our statements, in our proofs, our algorithms can have bugs in them. Our automated reasoning systems may not be doing what we want them to do. And without a semantics, you're not even wrong. So the phrase is often attributed to Wolfgang Pauli, who was critical of mathematical papers that were imprecise. But the point here is that if your system comes back and tells you that 2 + 2 is equal to 5, well, unless you've said what 2 is and what plus is, and so on, it's not even wrong. I mean, for all you know, maybe that's the intended behavior. And what's going on is that in ordinary mathematics, we tend to share a common understanding of what the correct rules of reasoning are. So when I talk about semantics in the foundational sense, what I mean is really having a formal system underneath. So having an explicit grammar for making assertions and some kind of explicit description of what the rules are.
The first one is that these are opinions. I only like something when I have this. All symbols have a proper definition in whatever framework you want. A fresh user who doesn't know anything. You need to tell them how to write terms. The sine of x, the integral of something. Just the Mathematica thing, right? The terms. You need to tell them how to write types. And if you have dependent types, of course, the types include terms. Okay? You need them to tell how to make those terms with types in them into statements. And then you need proof steps. So the first three are kind of easy. I mean, you write for x. So this is all light code, and I'm not supposing you can parse this on the fly. So I turned it into mathematical notation. I omitted all kinds of type-related noise, because I don't think that's too interesting. And then I got this. And then for all the statements that he got, this is about C17. And he proved it, most of it.
So it's not just, he didn't do the formal proof staging, he really gives me in his style the true proof.
One thing that's tricky to deal with in any foundational system are algebraic structures. And the reason is that we expect algebra to do a lot for us, right? So there are relationships between classes of structures, for example, every abelian group is a group, or you can take the additive part of a ring and that's an abelian group, and there are instances, the integers are an instance of an ordered ring, and there are constructions which take a field and the automorphisms gives you a group, right? So there are lots of operations and relationships between classes of structures. And the point is you want to reuse a lot. I mean, you don't want to have a different symbol 0 for every 0 around, or a different symbol for addition.
So one of the questions was about the importance of mathematical structures for mathematics. And I think they're absolutely crucial because they really are the nouns of mathematics. But in the same way, mathematics has verbs and adjectives and adverbs. And they're just as important. If you only concentrate on the nouns, you're only seeing a small part. If you ignore the nouns, of course, there's very little that you can actually talk about. So it's a lot more complex than just the structures. And without the structures, of course, there's kind of nothing to base yourself on. It actually forms a really complicated graph that has all sorts of cycles. And so the relationship of mathematics is interesting, especially because there's actually structures that are interrelated in cyclic ways, and hierarchy is a flat-out mistake.
Bringing the Gödel incompleteness phenomena into the 21st century is really, one has to compose these these concrete mathematical problems that are independent of the axioms. One has to compose them because we don't have the technology, we're not even close to having the technology appropriate for dealing with off-the-shelf mathematical statements in this way at the concrete level, concrete mathematical level. We don't have that technology. We may never have that technology. It has to be composition. And so I view myself as a composer of mathematics. And I think that if I were composing music, it might really interfere. So I feel like I should separate it. I don't perform mathematics so much. I compose it. And I don't compose music so much. I perform it. I decided early on, late teens, when I got my PhD, I decided early on that that this was the essential issue that needed to be addressed in the foundations of mathematics in order for it to survive as a vibrant subject at the level that Kurt Gödel brought it to us in the 30s. He brought it to an extremely high level of visibility and depth. And although further things were done, there was a understanding or thought that the phenomena that he uncovered was very limited. And that's all well and good. He did this great thing, but it has a limitation, and it's really part of the classic history of ideas, and it's not really relevant today, so to speak. And I thought that was false. In other words, there was no way to define what is a real, legitimate example of concrete incompleteness that is compelling mathematically. We still don't know how to actually define what that means. But when it's there, you can recognize it when you see it. I've spent almost 50 years coming up with examples of statements that are independent of the axioms that also have these features of mathematicians relating strongly to their naturalness and their content at the concrete level. And I sat down with both these mathematicians in detail, at least a half an hour with both of them, in detail at this meeting, whether it works for them, whether there's these new examples that I've come up with in the last, in fact this year, actually meet these criteria. And indications were clearly that they do meet these criteria, and I have not really had that kind of reaction up to this point. This is very encouraging.
Just saving time of mathematicians. You see, Hilbert asked for the algorithm to decide different equations, and many mathematicians actually tried to find such a method. But what I proved is that it does not exist. So all these efforts were in vain, and this result can be compared to the law of conservation of energy. Now that we know this law, nobody would spend his or her time by inventing perpetuum mobile. And that was just particular unsolvability or concrete problem. But understandability of different equations turned out to be a very powerful tool for proving other understandabilities in computability theory. It has many, many applications for other understandabilities. It seems to have nothing in common with the tenth problem. The tenth problem is about different equations, and the Riemann hypothesis is about complex zeros of so-called zeta function of Riemann. But it turned out that we can construct one particular different equation, unsolvability of which is equivalent to the Riemann hypothesis. And so, in a sense, this hypothesis is just a very, very special case of Hilbert's tenth problem. But in 1900, when Hilbert stated his problems, nobody anticipated such a relationship. It was discovered only much later when the tenth problem was shown undecidable.
We can retrieve meaningful geometric objects from the diagram image using shape recognition techniques. Minor meaningful geometric relations among the objects using numerical verifications, then formulate one or several conjectures using deduction and induction principles, and finally prove or disprove the conjectures using automatic theorem provers. In this way, hundreds of theorems, including geometry, have been discovered automatically from images of diagrams.
The other thing is that the diagrams definitely are statements. There are no statements that the diagram is this, the diagram is the statement. And of course, in category theory, it's like this. So I don't know any category theory, so please don't hold it against me. I found this in a book. It's supposed to be the proof of your lemma. So it said, your lemma, some statement, proof, this diagram. Box. That was it. I think that's from category theory. Also, this contour.
Also, math has a lot of traits that make it interesting. We need to understand it very, very precisely, which language technology has difficult with. It also has an enormous 100,000 words technical vocabulary, and that makes it interesting. The vocabulary changes over time. Every paper introduces new words.
So I see some well-enshrined problems in notation. The first one, of course, is whether 0 is in n. Everyone knows the answer to this question, and half the world thinks it is, and half the world thinks it isn't. There is actually an ISO standard on this subject, and I must confess I get slightly upset when people disagree, but simply because there is now an ISO standard. The ISO standard says 0 is in n, and n star is what you use for not if it doesn't have 0. That's what the ISO standard says. Every textbook chooses the branch cuts of a function as they're needed for the purpose. But in computerized mathematics, we have to follow the IEEE 754 standard and the branch cuts of natural logarithm, from which everything else is defined uniquely in a complex plane.
Partial functions arise quite naturally in mathematics. In traditional mathematics practice, an undefined term resulting from the application of a partial function is considered to be a legitimate but non-denoting term, so it doesn't have any value. An application of a function to an undefined term is considered to be an undefined term itself, and the application of a predicate to an undefined term is considered to be a false assertion. These simple rules allow defineness conditions to be expressed implicitly so that ideas involving partial functions and other sources of undefinedness can be expressed very succinctly. So this is what happens in standard mathematics. In standard logic, partial functions are treated as monsters that must be either avoided or disguised as total functions.
Okay, partiality. I put this at the front because it's my main hang-up and I want to get it across. Here's a statement. For each function f on the real numbers, there exists a finite number n such that the integral from minus infinity to plus infinity of that function f is less than n. Okay? Everyone has processed this. To put it into Holite, I need to do it symbolic with quantifiers, and then universal quantifier becomes an exclamation mark, and because it's ASCII, but it doesn't matter so much, and it's provable. You can prove it. And I find that very strange. I mean, that integral can diverge. How can it be finite? I mean, less than n sounds like it's finite.
When formalization serious work about formalization started, they wanted precise. There was, what are the real numbers and how can we really reason with, what are those? That's when we started really finding all that precision and formalization of mathematics. So we had Cauchy sequences and we have Dedekind cuts, excuse my German. And of course, there was the formalization of Cantor's set theory, and Peano was formalizing arithmetic, and Frege was the son of a mathematician who was reading these books, and he wasn't really happy with all the informal mathematics that he reads in the book. So at the beginning, he started with his Begriffsschrift.
De Bruijn is a professor, was a professor, he recently died, of mathematics who introduced the field of interactive theorem proving. He was the first guy who had the insight that computers really make this possible. No one believed him at the time. Okay, so he had this Automas group in Eindhoven where they built this system. And he had papers about this.
And he had this thing called mathematical vernacular. And the mathematical vernacular was, because he did Automas and he did many versions of Automas, many of the ones here are versions of Automas, but he didn't do the proofs. But then, of course, there was a mathematical vernacular because after a while he said, Automas is, Frege did all mathematics in logic and nobody really, mathematicians don't use logic, they don't want to use logic. And then came De Bruijn, Automas, and Mizar and everything, and still mathematicians don't use those systems because they want to do their mathematics without these systems. And then De Bruijn himself started, withdrew back a little bit and started the mathematical vernacular. The mathematical vernacular is not a full verification. It's simply, when you want to write mathematics, write it with a certain structure. And he even started writing his papers in mathematical vernacular.
One of the beauties of formalized mathematics is that they do not rely on reputation for correctness. So really anyone can contribute. In traditional mathematics, one tends to believe a theorem because it's been announced by a reputable mathematician. And there's quite a bit of controversy that has surrounded results that were announced by outsiders, whether it was the Poincaré conjecture or the ABC conjecture. Those happen to be actually correct.
There are many people who are deeply enthusiastic about mathematics, even if by training or by profession they're not mathematicians. And so I like to think there is. And one of the peculiarities of theorem proving is that the people who excel in it are perhaps often not so much the pure mathematicians, but more the computer scientists, because, shall we say, they have a taste for the kind of level of formality, the precision, just the fact that it involves a machine.
And I'll start with a little anecdote. So a student of mine last year gave me this little puzzle. Does there exist a function f from reals to reals such that blah, blah, blah? And I really wanted to solve it to impress my student. So I solved it on paper. But then I wondered, could we automate this? And what does a formal proof look like? And so on. So I came up with a sketchy proof. And then John Harrison gave me his simplified version of my proof, where I was using big summations and so on. He's like, you don't need any of that. So one is basically, it's given already. 4 is just a contradiction. Just need to come up with 2 and 3 here and here. You just need to instantiate and do a bit of reasoning. And of course, he gave me his Hall-like proof, obviously. I don't know, my hobbies don't look too much like my work, but in John's case, this doesn't apply, obviously.
there are some points of contact between computer games and formal proof. I almost feel that formal proof has a certain addictive quality that I suspect it is actually tapping into some of the same subconscious impulses that computer games do. I mean, you're given some limited rules or set of resources and you're trying to achieve some objective, whether it's you're trying to prove a theorem using a set of inference rules or you're trying to, you know, get through a dungeon and avoid the monsters. There really are some points of contact, and I think if we could get young people excited about theorem proving somehow, present it as a more game-like activity, or even the people who do puzzles like Sudoku or things like that, not quite games, but things like that, if we could somehow manage to warp what they're doing ever so slightly, it wouldn't look so far from proving theorems.
The main challenge to actually getting to formalize a large body of mathematics is to get enough people on board to make the experience of using a computer system to do this type of work enthralling enough that people will join in and collaborate in the effort. Another challenge is actually to get to a point where the efforts of everyone can be combined, that it doesn't get siloed in one system and the next system and the third system and so on.
The question is it possible to formalize an area when you don't have the previous areas formalized already? Let me make here the analogy of parallelism. If you have a single person working for 100 years, then this person could start at the very beginning and produce systematically everything. But if you have 100 persons working for 1 year, then we cannot have the second person waiting for the first person to finish. We will have to start at some intermediate point without having the previous results. We need modularization of these areas and agreeing on interfaces, etc., so that this can be done.
Mathematics is taught as a whole body of facts or as algorithms that you use to do certain kinds of computation. And that's not really what mathematics is. Mathematics is looking at the world, identifying mathematical aspects to it, and trying to figure out what's going on. So it's a very explorative, creative kind of process. If you give a normal person conjecture and say, can you prove this? They don't even know where to begin. They don't know what the rules of the game are. But if you build a library that you can interact with, then the rules of the game are built into it. And even very young people can try these rules out. They can do experimentation. They can build up their own models and see what happens. And these models could be very, very simple.
Mathematics is a great achievement of humankind. And I think it's very important for us to communicate that to the next generation. I think it would be very useful to kids of all, even if they don't become professional mathematicians, to understand better that that's what mathematics is. And I think we have a real responsibility as a profession to communicate that. I mean, not everybody can become a professional athlete, but everybody likes sports. I mean, not everybody can become a great musician, but we all like to sing. I mean, we don't stop people singing because they don't have the voice to become an opera singer or a big pop star. I mean, mathematics is something like that. We all have that capacity. We all can find joy in certain arguments.
Mathematicians have been very slow to utilize formal methods in their work for two reasons. First, most mathematicians do not see any significant benefit in employing formal methods. Second, contemporary tools for applying formal methods, such as proof assistance, are quite challenging to use because they are based on esoteric logical ideas and techniques and require extremely high level of attention to detail.
So I would like to mention some motivations from mathematics. Is of course one important reason is that if you wish to prove that something is not provable, then you need to do some formalization. And of course, consistent proof requires formalization, and Gödel's incompleteness theorem and reverse mathematics, and also Frankel set theory But I think these motivations are mainly theoretical. So mathematicians usually talk about formalized mathematics, but they do not work in it. So here, formalization of logic is important.
In my work at Intel, I have actually been doing proofs of, shall we say, computer artifacts, that is hardware, software, protocols, that kind of thing. And in particular for proofs in floating point arithmetic, it's very useful to have systems of formalized mathematics, because even, for example, to say what a floating point sign function does, you need to understand the mathematical sign function, because the whole idea is it's meant to be an approximation within some bounds, which we needn't get into.
Karl Weierstrass was assailed for his introduction of rigor into mathematics, and he was considered a poor teacher because of his rigor. Peano, who some regard as the founder of modern logic, insisted on using his formal language in his mathematics, even in his teaching, and he was also considered a poor teacher.
Euclid's characterization of Euclidean space, that's what we call it now, avoids numbers. And it was formalized in first-order logic much later by Tarski and others. So I found myself wondering, could it be formulated purely equationally in terms of operations instead of relations? Like, for example, Boolean algebras or groups or rings. So I was able to do this satisfactorily for the affine fragment. That's the fragment of Euclidean algebra that avoids angles and lengths. But to do it for the full theory with angles and lengths, I found I had to introduce a pasting operation to accommodate the resulting partial operations.
It's perfectly possible to imagine a world quite similar to our present world, in which nobody cares about any kind of proof. In particular, science and engineering do not really require proofs at all. They do require calculations, but that is something different. Now, let's consider whether correctness of proofs should be considered a social benefit. In their very own subject, minimal surfaces, there are fundamental results that were accepted for half a century, but finally in the last decade were judged to be wrong proofs. The Kepler conjecture and the flyspeck project are often cited as examples of successes in formalization, and one of the reasons that Tom Hales undertook the flyspeck project was that the social process didn't completely work for him. Although his paper solving the Kepler conjecture was published in a prestigious journal, that publication came with a codicil stating that the referees could not certify its correctness. The mathematicians think the probability of error is so small that although it would be awful if there were an error, it's not worth it to check the proof formally. We might compare this with the thinking of those who don't buy health insurance because they're healthy. The realization of the grand dream requires hundreds of man-years of effort to construct good systems to support formalization and to actually formalize mathematics. The QED vision would require, at a very minimum, to formalize the common core of mathematics, by which I mean those theorems that can be cited by name without giving an explicit reference. That more or less coincides with what's taught in undergraduate and graduate courses required of all PhD students. You can get a PhD, at least in Europe, for formalizing a certain part of mathematics. You'll get a computer science PhD, not a mathematics PhD. Nowhere in the world today can you get a mathematics PhD for formalizing a known proof. This raises the question of how the labor of finding informal proofs is paid for. You can get a PhD for proving a new theorem. The labor cost of one published paper is, I'm guessing, 3 months to 1 year, possibly less for a shorter paper. 5 or 6 of those papers may get you a tenure job or a merit increase. You may also get a social payoff in the form of reputation, conference invitations, the respect of your colleagues, maybe even job offers. If you were to stop writing new papers and instead formalize your former theorems, none of those payoffs would apply. So to summarize, ordinary mathematicians have absolutely no social or economic incentive to start producing formal proofs. That's the fundamental reason why the QED vision has not been realized. Nobody's willing to pay for it.
I suppose there are basically 2 aspects. There's the translation of informal statements into formal ones, and then there's the translation of your intuitive idea of the proof into a formal sequence of logical steps. So those to some extent can be done in isolation. I mean, in the software industry, in the world of software verification, there's a lot of interest in having a formal specification of software, even if you don't try to have any kind of formal process of proving that the software satisfies that specification. I think the contribution I'm most pleased with was formalizing this idea of you can assume something without loss of generality, because it's very convenient in geometry theorems to say, okay, you have this configuration of points in three-dimensional space, but maybe they all lie on a plane and you'd like to distinguish some point. And mathematicians often intuitively say, well, let's just assume the whole thing lives in R2, and let's assume A is the origin, and let's assume something else. And that's the sort of thing that would traditionally kind of strike terror into the hearts of formal people, because to justify that formally is not trivial. So I was quite pleased with coming up with a framework where you could automate that kind of thing, and I know other FlySpec people found that very useful. So out of the great 100 theorems on Frick's list, Holroyd has proofs of 84 of them, including things like Cayley-Hamilton theorem, the impossibility of trisecting an angle by the usual geometrical constructs, Dirichlet's theorem on primes and arithmetic progression, proof that E is transcendental, stuff about Fourier series, Minkowski's geometry of numbers stuff, the prime number theorem, very significant. That was first proved by Jeremy and his team using Isabelle Hollow. This one is the analytic proof. This is actually using Cauchy's theorem and a contour integral, Euler's polyhedron formula.
People who don't know this technology cannot imagine that this is possible. They think, come on, perfection is not attainable in the real world. They start talking about cosmic rays and hardware failing, and you make mistakes in your software coding, or there are all kinds of things that can go wrong in their imagination. And I don't think they really see how far we can get there. So the Tom Hales with the FlySpec project, or Georges Gontier with the Phi-Thompson theorem, or John Harrison with his theorems, those are really truly perfect. There's no flaw. It's like a diamond without any inclusions. It's just mathematics. But it's in the real world. It's in a computer memory. It's on a chip. It's on a hard disk. And I find that very attractive. I have this measure that it will take 140 man years to formalize all of undergraduate mathematics. So you take, the way I estimated this was I took all the universities in the Netherlands, I mailed them for their study guides, and I tallied what are the courses they teach. And they all had the same program, more or less. So I made a list, okay, these are the courses in a Dutch undergraduate curriculum. And then for every course I took a book and counted approximately how many pages there would be. And I had this measure that it takes about 1 week with the technology at the time to fully formalize 1 work week a page of mathematics from a textbook. And probably by now it's faster, but at the time. So then you do the arithmetic, like the Drake formula for alien life, and you get some number, and the number I got was 140 man years. So if you compare this with a Hollywood movie, it's about the same amount. So take any Hollywood movie that's in the cinema today, it costs about that amount of money. Okay? So it's not a big, if you think in this grand scale of things, it's not a big amount of money, right?
We say it's not about numbers. But in fact, it is about numbers, because indeed the amount of resources available to digitize mathematics is significantly less than the number of resources available to digitize cats.
So then I thought, okay, suppose someone would give me the money for 140 man years. That's about something like 50 PhD students. That's how I think of it. This kind of work is always done by PhD students. So a PhD student works in the Netherlands for 4 years, but he needs to write and there are other things. So he works for 3 years. 140 divided by 3 is 50 PhD students. Okay. What would I have them do? That's an interesting question. I would push for a project like this, and I wouldn't get there, but I would push for a project like this if I thought we had a future-proof proof assistant or a future-proof interactive theorem prover. But that is not there in a way that I think is ready for a project like this. Maybe other people will disagree here. So there's this new lean system, and the nice thing about lean is it's being designed, among others, by Jeremy Avigat. And he is both a hardcore Isabelle user and a hardcore Coq user. So most people are in one of those two camps, and they don't understand the other people. They cannot communicate. It's quite a different worlds. But Jeremy is transcending both worlds. So maybe Lean will grow into something that I think okay, now it's ready to do this project. And then of course I won't have the money. In the Coq system, 1 + 1 + 2 would be 1 dot. It's like, okay, this is immediate. Okay? In the whole system, you really need to do all the work. It's not hard right in. So the thing I was trying to get in this picture was, okay, how much proof is needed to get this thing? And there's this famous page from Principia Mathematica by Russell and Whitehead, something like page 300 something, where it says 1 + 1 is 2 in some shape, and people always use this in talks. Like, look, it takes 300 pages to prove 1 + 1 is 2. So, okay, now we have this new technology. In Coq, it's immediate, but in whole, how big is it? So I programmed the whole system to keep track of all the proof steps that are needed to get to 1 + 1 is 2. And I color-coded them, because there are different proof steps. Whole has 10 proof steps, so I had 10 colors. And then I put them in the shape of a long play record. Is that how you call this in English?
LP.
An LP. Okay, so it starts at the outside with the first proof step, and then it spirals in, and in the center, that's 1 + 1 is 2. And the nice thing is that you can really understand this picture in terms of the structure of the library. So there's another side to the picture that which I can give you if you would like to have it, where there's wiring. And you see all the wires going to things on the outside, because that's logic, that's reasoning, and it's all about reasoning.
For the Tom Hale's formal proof of the Kepler conjecture, which is called the FlySpec project, the number of such lemmas goes over 1 billion. So we have exported some important characteristics of this huge graph of lemmas and used various AI methods to select their smaller subset, which would be as good as possible for proving the next lemmas in that project. So in some sense, we are thus correcting or redefining the notion of important lemma implicitly produced by the human formalizers. This turns out to be feasible and useful. Even relatively simple ranking methods, such as, for example, PageRank, result in improvement of the overall theorem proving performance.
Lemma selection can have a big impact, right? So the lemma selector, you tell it, give me 16 facts or 16 lemmas, or you tell it, give me 1,000, and then you call automatic provers on it. And then we have different versions. We have 2 versions of Mesh, 2 versions of MASH, and 1 of Maple, which has no machine learning. You see the machine learning is better, and the Mesh is better in MASH, although we don't see it very clearly except with low number of lemmas. And what this shows is, right, you can be anywhere, right? If you're not careful with the parameterization, you'll select too few lemmas, or you select too many, or you select them with the wrong method, and you end up at a very different spot on this. So it shows how crucial this aspect is. So this is on some benchmarks. On others, you get slightly different curves and so on, but just to give you a flavor of how important this is.
In building Mathematica in the Wolfram language, we've gradually worked on formalizing a sequence of areas of mathematical thinking, so to speak.
This is still quite a new project. Let me show you quickly sort of the kind of information that we're gathering here. Name information, a definition of the space, notation, things like norms and inner products. And these are semantically encoded here. These are things that we can actually compute with and we can format. We have information about duality, isomorphic spaces, various identities and equalities, related results, which are theorems, classifications, right, which are mostly types of topological vector spaces, and reference information. So this is sort of a random sample of what we have. We have good coverage of LP spaces, CK, sort of all the usual stuff, and a lot of that I'd really never heard of before doing this project.
There's a question of how far we can go and can we encompass the kinds of things that appear in every sort of weekly collection of new research mathematics papers. That's what I was interested in learning, and I think one of the main things that I've actually learnt is that the state of the art in proof assistance systems and so on has advanced very nicely, and it's actually very encouraging the extent to which in those systems it's been possible to formalize a bunch of kinds of ideas that arise in pure mathematics that one might have thought were things that people who do pure mathematics understand, but which would not be amenable to some kind of rigid computer-oriented formalization.
So over the past 10 years, much of my research has been to try to figure out how computers could be used to express mathematics effectively. And in that time, I have acquired the conviction that this is indeed possible, and that the methods of software engineering could be applied to this task very effectively. More recently, the work of my colleagues in machine learning and artificial intelligence has developed to the point that it is very efficient at extracting meaning from unstructured documents. So this is probably the best time to try to take a large corpus of mathematics and convert it to a formal, precise form using the methods that have been developed painfully by hand. So the two big proofs that I've completed actually have fairly different size. The first project I did was actually a hobby. I'd been exposed to the four-color problem back in 1980 when I had a summer camp at Waterloo University. And I picked up the problem in 2000, tried to see whether I could actually do something with existing computer theorem proving systems. And it became sort of a labor of love over the next 5 years. The total effort probably involved about 20,000 actual lines of proof, and was done largely on my own. But having been successful, I tried to tackle a project that concerned real mathematics with the other theorem, which is a result in finite group theory. That's quite important because it basically started the much larger effort that succeeded in the classification of all finite simple groups. And that project took 6 years to complete using a team that varied between 8 and 10 people at any given time. The proof itself of the theorem itself was just about 45,000 lines. But in order to get to those 45,000 lines, we had to develop about 3 times as much material, basically formalizing a complete undergraduate curriculum in algebra and graduate curriculum in group theory. That effort had about 5,000 definitions and about 20,000 lemmas of various sizes.
Even when the full formalization is unattainable, it's an important ideal I maintain, because when you have a formal semantics, when you said things in a formal system, you know what your claims mean, you know what your goals are, and you know when you've accomplished them. Without it, maybe in practice to varying degrees, but with some degree of fuzziness, and at times when we're really imprecise, we're in the situation of not even being wrong. So even though it's an ideal, but it's, I think, a good ideal to aim for and keep in mind.
I tend to think of mathematics, the whole body of mathematics, as something that is a very, very human thing. Many mathematicians like to think of mathematics as something that exists in the abstract and we discover it. And I believe that we construct it. It's what we construct in order to make sense, to explain, to codify shortcuts in reasoning, to see to express that certain patterns of reasoning are the same in some places as in others. To, when we find new ways of thinking about something, to codify that so that we can communicate to others. It's really a language to talk about these abstract ideas that we think of and that we make up, and that are very useful and that make deep communication possible between us. But that's what mathematics is for me.
But mathematics in itself is one of the paths to beauty, as well as music or any other part of philosophy or any other part of a human culture. You get closer to sort of eternal and beautiful, and also to the human nature by doing mathematics.
The mathematics process is composed of three components: creating mathematical models that capture mathematical structure found in the world, exploring these models by proving conjectures and performing computations, and organizing these models by finding relationships between them. The goal of mechanized mathematics should be to provide mechanical support for all aspects of this mathematics process, not just for deduction and computation. And I would say it's not an exaggeration to say that mechanized mathematics has the potential to transform how mathematics is both learned and practiced.
Currently, the invention of new mathematics is done by mathematicians, human mathematicians, but in the meantime we understand our own process of inventing new mathematics in such big detail that we are able to automate invention and verification of mathematical knowledge. And so I'm pretty sure in a couple of decades, maybe even in 1 decade, maybe even now, it is possible to automate much of what we are doing now as mathematicians, the creative part of mathematics, and move on to higher and higher levels of inventing mathematics.
Perhaps one day computers will prove mathematical theorems and people won't understand the proofs because they are too long. We know from the work of Gödel that there certainly are short theorems with only very long proofs, with more symbols than there are neurons in the human brain. We would have no hope of understanding such proofs, but we might still like to know that the theorems they prove are true.
What I would hope to see an organization of mathematics that is accessible more to people than to computers, so it should be the computers that should be doing the adapting rather than asking the humans to adapt to the computers.
Mathematicians are rather conservative, and so computer science gives a lot of possibilities, and we need somehow to convince mathematicians that it is useful, that it's of help for them. It's not easy. We need to make an environment which is suitable for mathematicians. It's important for the success of the project.
So I think that computers will routinely prove simpler lemmas, suggest conjectures, and explore theories. They will also automatically understand later written texts and automatically proof-check them, possibly reporting major gaps and suggesting more precise similar statements that are provable. So I'm obviously biased, but I think that there is no doubt that machine learning from large corpora of both human and computer-found proofs will be extremely useful. Thinking that we can explicitly program all the theorem proving and formalization tasks without learning from previous knowledge is, in my opinion, as naive as thinking that we can explicitly program, for example, image recognition, chess playing, and language translation.
The thing that computers can, in principle, do, if the knowledge is sufficiently explicit, then we would be able to actually delegate the search for these representation theorems to machines. My kind of secret dream is when I retire in about 20 years, that one of these viewfinders, which one of my students is actually working on, will actually produce 1,000 theorems a week that I can publish.
So when you look at the history of mathematics, you see a history of people trying to find creative ways to extend the range of what we can think. We're cognitively bounded agents, and there's only a limit. There's a limit to how much we can keep in mind at the time, how much we can remember. But what we do is we try to develop concepts and ways that extend our cognitive reach. And in that respect, the computer is a game changer. It changes the kinds of proofs we can discover. It changes the kinds of calculations we can do. It changes the kinds of things that we can come to know. For that reason, I can say with certainty that that over time the computer will become more and more prevalent and central to mathematics. I don't know whether it'll be 20 years or 200 years before formal methods are commonplace in mathematics, but it will happen if the planet survives that long, because that's, in mathematics, that's what we do. We just find ways to think better and think more efficiently.
As far as I'm concerned, this workshop was a big success. There were people from, very distinguished people actually, from several different communities, from computational mathematics, from actual mathematics as it's practiced by pure mathematicians, and from the proving and theorem-oriented community. It's very rare that they come together, and for me at least, it's been very valuable and terrific to see the Sloan Foundation taking leadership in helping to bring these three communities together.